video, we're going to discuss the integration technique referred to as substitution. So this technique is going to allow us to integrate functions that are more complex than the functions we've looked at so far. So specifically, integration by substitution will allow us to integrate functions that resulted from differentiation via the chain rule. So remember, when we integrate a function, we're assuming that that function represents a derivative, and we're asking the question, what previous function would we have had to differentiate in order to end up with the function that we are integrating? So the focus is on how did we get that particular function via differentiation. So if that function resulted via differentiation with the chain rule, then this particular integration technique is going to allow us to work backwards and find its antiderivative. So let's just recall what we know about the chain rule. So if we were to differentiate with respect to x, a nested function, more specifically we call that a composed function, f of g of x, where g of x is our inner function and f is our outer function, then the derivative looks like the following. We'll have the derivative of the outer function, so f prime, with the inner function plugged in, and then we also multiply by the derivative of the inner function. So if we see a function of this particular form, then we know that it resulted from differentiation via the chain rule. Okay, so if we were to flip this relationship, we take the derivative of a function, get its derivative given by this particular function. If we anti-differentiate or integrate the derivative, then we get back to the function that we started with. So another way of saying this is the antiderivative of a function that looks like what we have on the right-hand side. So f prime of g of x times g prime of x integrated with respect to x. If we were to take the integral, the antiderivative of a function that looks like that, then we reverse the differentiation and we get back to our original composed function, f of g of x. So this means in order to integrate some kind of nested function, something where we have a function with another function subbed into it, then we must, number one, identify the inner and the outer functions. In other words, we need to identify how one function is nested inside of the other, which function is on the outside and which function is inside being plugged into it. And also, based on the form that we need, based on the form we see right here, that comes from the form that we get from differentiation with the chain rule, we also have to have the derivative. We have to have the derivative of the inner function present as a factor in the function that we're attempting to anti-differentiate, to integrate. So we identify our nested function. We have an outer function and an inner function. And then in order to take the antiderivative using this technique, the substitution technique, we also have to see the derivative of the inner function present in the whole function that we're differentiating. Now, we may not have the entire derivative, but we need to have some multiple of the derivative. So we may be missing a constant factor. Maybe the coefficient is wrong, something like that. But we're looking, for instance, for maybe a power of x that's specific, something of that nature. So we're looking for something that's very closely related to or completely equivalent to the derivative of our inner function g of x. Now, when we identify the inner function versus the outer function, that's what we're going to substitute. So we're going to make a substitution of the form u is equal to g of x, which is our inner function. So wherever we see our inner function, we're going to substitute the variable u. Now, u is ultimately an arbitrary choice, but for some reason we tend to use the variable u when we're talking about the substitution strategy. So I'm going to consistently use the variable u when we talk about substitution. Now, when we do this substitution, we change the variable in the problem. We change the variable of integration. So when we substitute for g of x, essentially we're eliminating x, and in place of x, we now have the variable u. So that means we also have to substitute for the differential. Now what is that? What is the differential? The differential is dx. dx tells us, among other things, what we're differentiating with, or what we're anti-differentiating with respect to. So when our function contains the variable x, we're taking the integral, we're taking the antiderivative with respect to x. When we substitute, we're eliminating the variable x and replacing it with the variable u. So we also have to change the differential in order to indicate that the variable of integration is changing, that we've changed the variable overall. Everything has to be in terms of that new variable. So this is going to be, in some ways, the most important part of the substitution technique. We have to make sure we appropriately substitute for this differential, which is ultimately going to make the mathematics work out the way it needs to. So the process of doing that substitution is as follows. So of course, we have decided what our inner function is, and we've determined that we're going to substitute for that inner function with the variable u. So we know what u is. U is now being substituted in place of g of x. Well, if u is substituted in place of g of x, then when we take its derivative, we have du dx, the derivative of u with respect to x, is equal to g prime of x, just because we're taking the derivative of both sides, so the derivative of u with respect to x, and then another way of writing the derivative for g would be g prime of x. So the goal is then to isolate one of the differentials. Now you'll see a couple of differing strategies for how you replace the differential. I'm going to show you the approach that I like to take just because more than likely it'll be a little bit simpler for you. It's more of a direct substitution kind of method. But ultimately what we need to be able to do at this point is we need to be able to solve for the differential du and the differential dx. In other words, think of this just like a fraction, and imagine trying to isolate the numerator and imagine trying to isolate the denominator. So that's going to give us two different expressions. So if we isolate du, all we would have to do is multiply both sides by that denominator dx and move it over. So we have du is equal to g prime of x dx, whatever that happens to be, based on what the function gx is and then its resulting derivative is. Now, a lot of textbooks, potentially our textbook, will have you substituting in this manner. In other words, finding g prime of x dx and directly replacing it with du. Now, another strategy is if you were to then manipulate this expression and solve for dx instead, you can just directly replace dx, and it's going to work out the same way, but in some ways the substitution may be a little bit simpler for you. So if we wanted to then isolate dx, well, all we'd have to do is divide by g prime of x on both sides and move it over. So we would also get that dx is equal to du divided by g prime of x. And so this is ultimately how we're going to substitute for our differential. So where we see dx in our antiderivative problem, we're going to substitute with the expression involving du and the derivative of g with respect to x, g prime of x. And special things are going to happen when we sub in g prime of x. A couple things in the formula are going to eliminate, and essentially everything that contains the variable x will go away, and everything that remains will contain the variable u. So after substituting, we're then able to integrate, because ultimately what we will have done is we will have simplified our more complicated antiderivative problem so that it's now in terms of a new variable, but a simpler function with that new variable. However, at the very end, we have to remember to resubstitute for the original variable. So when we take everything involving x and replace it with the variable u, we've changed the variable in the problem. And so ultimately, when we integrate, we've done what we need to do, but we don't actually have the answer to the problem. We don't have the actual integral. We have to resubstitute using the substitution that we assigned. So wherever we see a u at the very end, we'll then replace it back with whatever g of x was equal to. And we need to also keep in mind, if we are evaluating a definite integral, in other words, we have limits of integration, And we're not just finding the class of antiderivatives in general. If we're finding a definite integral with those limits of integration, we have to keep in mind the limits only apply to the original variable. So when do we actually plug in those limits of integration and evaluate the definite integral? Well, we're going to do that after we resubstitute. So we're only going to sub in those values once we're back in terms of our original variable, whatever happens to be more than likely x. So before we go through the whole procedure, let's just work on finding these two values, the expression for du and the expression for dx, involving a few different functions. Okay, so imagine we determined what we were going to substitute. So we have a nested function, f of g of x. We found the inner function, we found the outer function, and we're making a substitution for our inner function. We have 4 different substitutions. So based on that, we want to find du and dx for each of the following. In other words, find the expressions that we could use to substitute for our differential and change our variable of integration. So for our first function, inner function, we have u is equal to x cubed. So again, think of this like the inner function we're replacing with the variable u. So if we want the differential with u and the differential with x, the first thing we need is the derivative. So we need to differentiate both sides of this substitution relationship. So I'm going to take the derivative of u with respect to x, and then I'm just going to take the standard derivative with respect to x on the other side, and we know that's going to be 3x squared. So based on this relationship, we can now solve for du, and we can solve for dx. So du will be quickest to solve for. Again, all we need to do, exactly what we did up here in general, is we moved the denominator over, multiplied both sides by dx, and that gives us our expression for du. So if we were to multiply by dx, move it over, we then have du is equal to 3x squared dx. Okay. And then if we want to solve for dx, well, now we can just divide by 3x squared, which moves it over and isolates dx. So equivalently, dx will be equal to du divided by 3x squared. So those will be the two expressions for our 2 different differentials. And again, how we substitute will vary just depending on who's showing you this technique. In general, I like substituting directly for dx. So in other words, wherever we see the dx in our antiderivative, we're now going to replace it with this expression involving du and involving our original variable x. Okay, let's try a few more. So what if u is equal to 2 minus x squared, and we want du and dx? Well, again, we need to differentiate. So I'm going to take the derivative of u with respect to x. I'm also going to differentiate the other side with respect to x, and that's going to give me negative 2x. Okay, so if I want my 2 differentials, du, I can just move dx over, multiply both sides. So du is going to be negative 2x dx. And then if we want to solve for dx, divide the negative 2x. So dx, divide the negative 2x, move it over. It's going to be du divided by negative 2x. Okay, now what about some more exotic functions? We talked about natural log, we've talked about e. What happens if we want du and dx in this case? Well, same approach. So take the derivative with respect to x. The derivative of the natural log function is going to be 1 over x, so slightly different. Okay, so what if we want du? Same approach, move dx over, multiply both sides. So we can either write that as 1 over x dx, or we could think of dx as just going into the numerator, and we could also write it as dx over x. That would also be another way to write it. Okay, and then if we want the differential dx in terms of du, we multiply both sides by that x, move it over. So dx is equal to x du. Okay, and the last one. This one's a little bit more complicated. So look, it's an exponential function, but inside the exponential function is another function, which means if we want to differentiate this, we have to use the chain rule because this is also a function inside of a function. Not to worry, we know how to do that. So we're going to take the derivative of u with respect to x. Okay, so for this function, our outer function is the exponential function with e. Now we know when we differentiate an exponential function with a base of e, it's its own derivative. So the derivative of e to the x squared is going to be e to the x squared. But we know because there's now an inner function other than just x, that we also have to multiply by the derivative of that inner function x squared. And so we're going to multiply by its derivative, which is 2x. And just rearranging that a little bit, that's going to be 2x times e to the x squared. Now it doesn't matter that this is more complicated. Isolating du, isolating dx, that's just a matter of basic algebra. Moving things to the left, moving things to the right, using our inverse operations. So du, we're going to take dx, multiply, move it over. So that will be 2x e to the x squared times dx. And then if we want to isolate dx instead, well, now we're going to divide by 2x e to the x squared. So we'll have du divided by 2x e to the x squared. Okay, so all of this to set us up for this technique involving substitution. So again, what do all of these represent? U equal to some expression involving x, that represents the substitution we're going to do for our inner function. So let's review the technique real quickly. We want to look at our function that we're anti-differentiating. We're going to see a nested function that's going to have an inner function and an outer function. And we should also see the derivative of the inner function, so g prime of x. Now again, it may not be exactly the same as the derivative, but it's got to be some constant multiple of it. So maybe we're missing a coefficient, or maybe we have a coefficient that we wouldn't have otherwise just in the standard inner function's derivative. But we have the same function of x, essentially. So x squared, maybe we have a square root of x, something like that, specifically related as the derivative of the inner function. So once we identify our inner and outer function, we're going to replace our inner function with a substitution variable. We're going to use the variable u. So wherever we see that inner function, g of x, we're going to replace it with a new variable that we're calling u. We also have to replace our differential dx in order to change the variable of integration. In order to indicate that now we have a u in the problem, we need to differentiate with not with respect to x, but with respect to u. So we can take the derivative of the expression that we're substituting. So we have the derivative of u with respect to x is equal to g prime of x, the derivative of our inner function. And then we can either solve for du and substitute in that manner, or what I'm going to show you to do is to solve for dx and substitute directly for dx. Now once we have the substitution, in other words, once all the instances of the variable x are gone and all we have is in terms of u, then we can integrate. We'll have a simpler function, albeit a function with a different variable, and so we'll integrate using the techniques we've looked at so far. Once we have our integral, then we can resubstitute using the original substitution we did, and essentially we're done. We have our integral. So let's try several examples. This is one of those techniques that we just need to practice. We just need repetition. So we're going to do several different examples, different kinds of nested functions. Okay, so we want to evaluate each indefinite integral by first making a substitution. And of course, we want to write out what substitution we made, and we want to make sure we list all the steps we use to substitute, not only for our inner function, but also for the differential. Okay. So what are we looking at here? Well, I see a product of two functions. I see 3x squared maybe as one function, and then x cubed plus 1 to the 10th power could be another function. But specifically when I look at x cubed plus 1 to the 10th power, I see a composite function. I see one function inside of another. So we could think of x cubed plus 1 as an inner function, and then taking that and raising it to the 10th power represents the outer function. Well, we know now in order to use this technique of substitution, if we identify an inner function, we also need to have its derivative present. So if we're thinking of x cubed plus 1 as our inner function, well, what would we get if we take its derivative? Well, if we were to just take the derivative of x cubed plus 1, we would get 3x squared. And notice that's what we have right here. We have the derivative of the inner function as a factor. In other words, it's multiplied by what we have in the rest of the problem. So we have exactly what we need in order to use the substitution technique. So in order to substitute, what I'm now going to do is identify again my inner function, x cubed plus 1, and I'm going to reassign that the value of u. So I'm going to replace my inner function with a new variable. So u is now going to be assigned the value of the inner function, x cubed plus 1. So wherever I see x cubed plus 1 in this problem, I'm going to be able to put a u instead. So that's going to take this inner function, it's going to make it a u, and then we'll just have u to the 10th power. Now, before we can proceed at that point with integration, we have to change the variable. So dx tells us we're differentiating, or excuse me, anti-differentiating with respect to x. But when we put u in the problem, we're anti-differentiating with respect to u. So here's where we use that strategy, taking the derivative of both sides, finding du, finding dx. Okay, so based on this being my inner function, what I'm going to substitute for, I'm going to take the derivative of both sides with respect to x. So on the left-hand side, I'll just have du dx. And on the right-hand side, when I take the derivative, I get 3x squared. And notice that was also something we had in the problem. Okay, so based on this, I now want to solve for the individual differentials. We don't see du dx here, we see just dx, and then potentially just du. So if I want to solve for du, I'm going to move dx over. So I have du is equal to 3x squared dx. And then if I want to solve for dx, well, I can just divide both sides by 3x squared. So we'll have dx is equal to du divided by 3x squared. So we now have something that we can substitute in place of x cubed plus 1, which is the ultimate goal, to be able to substitute for that inner function. So this will be replaced by u. So just writing what we have, what we can now substitute for, 3x squared, we don't have a direct substitution for that. But x cubed plus 1, we're going to replace that with the variable u, so this will be u to the 10th power. And then dx, we're now going to substitute with the expression du divided by 3x squared. Okay, so in some ways, where we are right now kind of presents a problem, because now we suddenly have two variables in the problem. We had one before, now we suddenly have two. But something special happens based on this relationship between the function we substituted and then the derivative and then the differential that we substituted. Because notice what we have, the expression involving x that we'd like to get rid of so that everything can be in terms of this new variable. Well, it's complemented by something that matches in what we substituted for the differential. So you can think of this like a 3x squared over 1, and then we have a du over 3x squared. So essentially, if there's a numerator and a denominator that's implicit, then we have a matching factor of 3x squared in the numerator and in the denominator. And so it ends up reducing down, dividing out to 1, which leaves us with u to the 10th power and then just du. In other words, a brand new antiderivative only involving the variable u. And so the goal of substitution has been achieved. The goal of substitution is to take something that looks like this, a complicated function, and simplify it down to something much simpler, something we don't need special techniques to integrate. So now we can integrate this with respect to u, not with respect to x, but with respect to u, just using the rules we already have. So this is going to involve the power rule. We increase our exponent by 1 and then divide by that new exponent. So that's going to be 1 over 11 times u to the 11th power plus c. Don't forget our constant of integration. Now this is not quite our final answer because we're not in terms of the same variable that we had at the original problem. We had an x in the original problem, and this answer is in terms of the variable u. So this is when we're going to resubstitute. So once we've done the integration, we're then going to resubstitute using the expression we have for u, and that'll put us back in terms of our original variable. So in place of u, we're going to resubstitute our inner function, x cubed plus 1, and we have our antiderivative. So our final answer, 1 over 11 times x cubed plus 1 to the 11th power plus c. Now for this one problem, just to show that this has in fact worked, that we did in fact get the correct antiderivative, we know we can check our answer by differentiating. It's interchangeable in terms of the relationship. If we take an antiderivative, we get back to an original function. If we take this original function and differentiate, well, we get back to the function that we integrated. So we can check and make sure that this answer is actually correct by differentiating it and making sure we get back to where we started. So we don't absolutely have to do that, but it's not a bad idea to do it this one time just to verify that our technique did what it was supposed to do. So we're taking the derivative with respect to x of our function, so 1 over 11 times x cubed plus 1 to the 11th power plus c. Okay, so the first term we differentiate with the chain rule. Not surprising, because remember the technique we used here, we originally said it was related to the fact that we have a derivative that came from the chain rule. Okay, so it makes sense we have to use the chain rule right here. Now c is just a constant. It's an unknown constant, but it's a constant. So remember, when we differentiate that, it goes to 0, it disappears. So we're just focused on this first term where we use the chain rule. So we differentiate the outer function, which is something raised to the 11th power, which says bring down the exponent, so that becomes 11 over 11. In other words, the coefficient goes away, and then decrease the exponent by 1, which will take it to 10, and then we'll have the inner function inside of the outer function's derivative. Okay, but because this was a nested function, we have that inner function as well. We also have to multiply by the derivative of the inner function, which is 3x squared. And if we just rearrange that a little bit, that would be 3x squared times x cubed plus 1 raised to the 10th power, which is exactly what we started with. So that verifies that we did in fact find the correct antiderivative. So that's the general idea behind substitution. So let's walk through just the process one more time, and then we'll try a few more examples. Okay, so the original idea, we're looking for a nested function, one function inside of another. So x cubed plus 1, all raised to the 10th power, was our nested function. So the inner function was x cubed plus 1, and the outer function took that and raised it to the 10th power. And we also noticed that if we were thinking of x cubed plus 1 as our inner function, then 3x squared was the derivative of the inner function, which is important. In order to use substitution, not only do we have a nested function, but we need to also have the derivative of the inner function present in the problem. So noticing that, we then substituted for x cubed plus 1. So we determined we're going to make the substitution. In place of x cubed plus 1, we're going to put the variable u, and so this becomes u to the 10th power. But once that variable changes, the differential changes as well. So we differentiated the equation we have for our substitution, and then we solved for du, we solved for dx, we replaced dx with what we just found, and one result of that was that anything that remained that contained the variable x was then eliminated, leaving us with an antiderivative in terms of the variable u. And so we anti-differentiated in terms of u, and then replaced using the original substitution in order to get back to our original variable. So every problem that we do with substitution is going to look roughly the same. It's going to be some variation of that kind of technique. Now, in some ways, the challenge is recognizing what's the composite function. What's the function that has an inner component and an outer component? Here, there's very clearly something that has an inside and an outside, but it's not always going to be that obvious. So for instance, the next problem, we want to take the antiderivative with respect to x of 2x divided by 1 plus x squared with respect to x. Now there's not an obvious inner and outer function here. So in order to determine what the inner function might be, we may have to do a little bit of work ahead of time. So let's think about another way that we could write this, particularly with that denominator. We know that anytime we have a denominator, another way to write something that's in a denominator is by rewriting it with a negative exponent. So another way of writing this expression is 2x times 1 plus x squared to the negative 1 power. That's another way of saying that this expression is in our denominator. And by writing it in that manner, now we can see what looks more like a nested function, an inner function inside of an outer function. And so that's going to give us a hint about what we'll substitute for. Now again, if we think of 1 plus x squared as our inner function, then in order to use substitution, we need to see the derivative of that inner function also present in the problem. So if we were to take the derivative of the inner function, 1 plus x squared, we would get 2x, which we also see right here. So that means that this particular function is structured in such a way that we can use substitution. So now we're going to make our substitution for our inner function. So we're going to let u be 1 plus x squared. Okay, so wherever we see that 1 plus x squared, we're going to replace it with u, which will simplify that quite a bit. But we also have to replace our differential to indicate the new variable of integration u. So in order to have something to replace for dx, I'm going to take the derivative using the expression for my substitution. So I'm going to find du dx, and based on the function that it's equal to, that's equal to 2x. And so if I isolate du, I'm going to have 2x dx. And if I isolate dx, I'm going to have du divided by 2x. So not only am I going to replace my inner function, but I'm also going to replace my differential with du over 2x. So let's make that substitution. So we still have our 2x out front, but remember everything kind of worked out the way it needed to in the end for the previous example. So that leaves us with u to the negative 1 times dx, which we're replacing with du over 2x. Okay, so we have our new function in terms of u, we have the correct differential. Based on the relationships we see in this problem, the remaining factor involving the variable we wanted to replace cancels out, and so we're just left with u to the negative 1 du. Now I'm going to go ahead and write u to the negative 1 as 1 over u again. And the reason I'm going to do that is because when I look at it like this, u to the negative 1, I'm tempted to want to integrate that using the power rule. Well, what does the power rule do? What would it tell us to do? It would tell us to take our exponent and increase it by 1 and then divide by that new exponent. Well, what would happen if we did that? If we increase this exponent by 1, well, negative 1 increased by 1 would go to 0, and we'd be dividing by 0. So that rule doesn't actually apply here. Why is that? Well, u to the negative 1 can also be rewritten as 1 over u. And remember, the integral for this particular expression, that was a special case. It was represented by a special function. So in this case, the function we would get would be the natural log function. So when we anti-differentiate, we get the natural log function. So the antiderivative is going to be the natural log of the absolute value of u plus c. Now, why do we need the absolute value? We need the absolute value anytime there's a possibility that what might go inside the natural log is actually a negative number. The natural log of anything less than or equal to 0 is actually undefined. Now, what's going to take the place of u? We're going to replace u with 1 plus x squared in order to get back to our original variable. So let's think about 1 plus x squared. Suppose I were to plug in a negative number, which seems like the only possibility where we might have something negative inside of the natural log function. Well, if we plugged in a negative number, we would still get a positive output because we're squaring it. Even if we plugged in 0, 0 squared would be 0, and then we'd add on 1, and it would be a positive number. So as it turns out, based on what we're substituting into the natural log function, this expression 1 plus x squared, 1 plus x squared will always be positive. We never run the risk of what's inside of this natural log function becoming negative. So as it turns out, because of what we're plugging in here, because it's always going to be positive, when we sub it in, we can actually drop off the absolute value bars because this expression will always be a positive number. So we're going to resubstitute. So we have the natural log of 1 plus x squared plus c. That will be our antiderivative. Okay, let's try another one. Similar to this one, just a little bit more complex. Stepping up a notch. Okay, so we have the antiderivative with respect to x of x cubed divided by 1 plus x, 1 plus x to the 4th quantity raised to the 5th power. Okay, so I see a nested function, but I also see it in the denominator. So 1 plus x to the 4th is nested inside of x to the 5th, but that's also in the denominator. So just like in the previous example, it might not be a bad idea to go ahead and rewrite this real quickly, just using a negative exponent. Since we know this may be something where the power rule applies, and that's going to put this in a form where we can use the power rule. Okay, so we can definitely see our inner function. Now we know in order to use substitution, we're going to replace that with the variable u. But in order for this to work, we need to see the derivative of that inner function present in the problem as well. So what happens if we differentiate 1 plus x to the 4th? Well, we're going to get 4x cubed. Well, I don't actually see a 4x cubed in the rest of the problem. I do see an x cubed, but I don't see a 4x cubed. The problem is not really a problem. It's not really an issue, the fact that we don't identically have the derivative. We don't have 4x cubed, which is the actual derivative, but we have x cubed, which is a multiple of that derivative. What we're focused on is what's happening to the variable x in terms of finding the derivative present or not present in the function. So differentiating, we get 4x cubed. As long as we have the x cubed part, we're good. The constant out front that we would need, or in this case the one that we're missing, is not going to make a difference. And I'll show you why once we actually get to the point of making the substitution and simplifying things down. So because we have something closely related to the derivative of our inner function, we can proceed. So we're going to substitute for our inner function, 1 plus x to the 4th. So in order to change our variable of differentiation, we need our differential. Excuse me, I said differentiation, anti-differentiation. So we're going to take the derivative, so that's going to be 4x cubed. And again, isolate our two differentials. So du is equal to 4x cubed dx, and then divide the 4x cubed, and so we get dx is equal to du divided by 4x cubed. Okay, so we have something to substitute for our inner function. We have something to substitute for our differential. And then we still have something involving x, but let's see what happens in this case when we substitute. So we have x cubed, we have our inner function raised to the negative fifth power, and then substituting for dx, we're going to replace it with du divided by 4x cubed. Now we saw in the previous two examples that any remaining expression involving x reduced down, that it divided out. That happens here as well, but not quite in the same way. So the x cubed here, the one we had in the original problem, is complemented by 1 in the denominator. So that actually cancels out. But notice we still have a 4. The 4 remains. So why is there something left over? That's because, again, we didn't have identically the derivative of our inner function. We had a multiple of it. So when we replaced that differential, that constant was left over. The constant that we didn't have in the beginning, that we couldn't cancel out over here, was left over in our denominator. But we know that a constant is not a problem when we're talking about differentiating or anti-differentiating. So let's rewrite everything we're left with. Now, if we're left with a 4 in the denominator, that's another way of saying that we're left with a factor of 1/4. So we have the antiderivative of 1/4 times u to the negative 5 power du. Well, if it's a constant factor, we know that we can pull that out of the antiderivative because it doesn't actually affect the result for anti-differentiation. And so it does not present a problem. So we can just anti-differentiate like normal, and then we'll deal with the 1/4 at the end. So increase our exponent by 1, which would take us from negative 5 to negative 4, and then divide by that new exponent. So that's going to be negative 1/4 u to the negative 4, and then we're adding on c to that. Okay, so let's see if we can clean all of this up in one step. I think we can do it. So first off, when we multiply those two constants together, there's going to be a negative. So it's going to be negative 1 times 1, which is 1, 4 times 4, which is 16. So there's a coefficient of negative 1/16. Now we also have u to the negative 4. Okay, so here's our u. We're going to resubstitute. So it'll be this expression to the negative 4 power. But we know a negative power will then move something down to the denominator. So our expression 1 plus x to the 4th that is then subbed back in is actually going to be in the denominator. So of course normally we'd put the 1 in the middle, but just to do it all in one step, it kind of ends up at one end, not a big deal. So we have our numerator, we have our denominator, and again, where did this come from? We resubbed in for x in place of u to put it back in terms of the original variable, but the negative exponent said whatever we sub in, remember it's going to go to the denominator, and so this is the expression we end up with, plus c. So that is going to be our antiderivative in this case. Okay, the next one, we're going to have to be a little bit more creative. Okay, in terms of an inner function and outer function, we do see an inner function and an outer function, but that is not actually what we're going to differentiate, or substitute for in this case, and then differentiate. So ln of 3x over x differentiated with respect to x. Now I see an inner function and I see an outer function. So that's good. Okay. So normally I would think I'm going to substitute for the 3x because it's an inner function, it's inside of the natural log function. But remember, in order for that to be helpful, in order for that to be possible, we have to see the derivative of that function as a factor in the bigger problem. So if we think of 3x as our inner function, we're looking for its derivative as a factor there in the problem. So its derivative would be 3. Okay, so we would have a 3, not a problem. But that doesn't tell us what would happen to this x in the denominator. Because remember, for instance, with the one we just did, when we substituted for our differential, we then were left with something that canceled out anything that remained involving the old variable, leaving us with something entirely in terms of our new variable that we got from substitution. And that happened because we had something related to the derivative that was already there in the problem. Well, if the derivative of this inner function is just 3, then we're not going to have anything that's going to eliminate that x in the denominator, which is a problem. We'll substitute and we'll end up with something involving u, but we'll still be left over with this expression involving x. So if we try to substitute by letting u equal that inner function 3x, then we're going to end up with an expression that involves not only u, but also still involves the variable x, which means the substitution doesn't actually accomplish anything. Well, as it turns out, there's actually another way we can use substitution in this case. So think of it more generally. Think of it as we're looking for a function in this problem that also is matched by its derivative in the same problem. Well, I see my natural log, a natural log of something, and I also see an x in the denominator, which we can think of as 1 over x. So I'm going to rewrite this in a slightly different way. So another way of thinking of this is natural log of 3x, and we also have 1 over x in the problem. Well, I know if I were to take the derivative of the natural log function, then I would have 1 over x. Even if I were to take the derivative of the natural log of 3x, as it turns out, its derivative is still just 1 over x. So I have a function and I have its derivative. The function that I have here, whose derivative I also see, happens to itself be a nested function. But again, the focus is more on looking for a function whose derivative we also have in the problem. So natural log of 3x is a function whose derivative we also see in the problem. So that means rather than replacing 3x, what seems like very much an inner function versus an outer function, rather than replacing 3x with u, rather than making that substitution, we're actually going to make the substitution where u is equal to the natural log of 3x, the whole thing. And again, why is that? That's because this function, natural log of 3x, we see its derivative. We're looking for a function who's matched with a derivative, matched by its derivative, and that's going to indicate what we want to substitute for. So I'm going to allow u to be natural log of 3x. So just to prove that what we expect to happen does in fact happen, what happens if we take the derivative of this function? Well, the derivative of the natural log function is going to be 1 over whatever is inside of it, so 1 over 3x. But because we have something slightly more complicated inside, we have a nested function, we also have to multiply by the derivative of whatever is on the inside, which would be 3. And notice in this case, those 3's cancel out, and we're just left with 1 over x, which is exactly what we have right here. So we have a function as well as its derivative. So that's a good indication that this substitution will be an appropriate one. And so solving for our differentials, we have du is equal to, move the dx over, so 1 over x dx. And then if we want just dx, we'll move the x over, multiply both sides. So we have dx is equal to x times du. And so now we can substitute. We can replace the whole natural log of 3x with our variable u. So that's going to become u. We have our 1 over x, so times 1 over x. And then we also have our dx, which we're now replacing. And we're replacing that with x times du. And again, because of the relationship we saw right here, the fact that our derivative is something that's already in the problem, the result of substituting with that new differential is now everything that remained that involved our variable x is eliminated. And so we're left with the antiderivative of u with respect to u. So this is now something we antidifferentiate using the power rule. Remember, there's an understood 1 right there. So we increase that exponent by 1 and then divide by the new exponent. So 1/2 times u squared plus c. So u we define to be the natural log of 3x, so we're going to substitute that back in. So that's going to be 1/2 times the natural log of 3x quantity squared plus c. And we can put the parentheses around the 3x if that helps. So that will be our antiderivative. Okay, let's try another one, also involving the natural log function. Okay, a little bit different. So previously we had the natural log of 3x quantity over x, and then we also here in this case have the natural log of x cubed over x integrated with respect to x. And we have a hint here. Hint, consider using a logarithm rule to simplify first. Okay, why is something strange going on here? Why do we need to use a hint in this case? Why can't we just substitute the same way we did a moment ago? Well, if we were to substitute number 1, suppose we wanted to use x cubed as our inner function, like we would normally intuitively do. Well, we need its derivative here in order for the substitution to work out the way it's supposed to. But the derivative of this inner function, x cubed, would be 3x squared. And we don't see a 3x squared or an x squared in this problem. All we see is an x, and it's in the denominator. So there's nothing that will cancel out if we were to substitute for x cubed as our inner function. Well, what if we were to substitute for the whole logarithm like we did before? So suppose we were. I'm going to write it up here, and let's see what would happen if we tried to do that. So suppose we allowed u to be the whole natural log of x cubed. What happens if we take the derivative with respect to x? Well, remember, same rule, so we have 1 over the inner function, whatever it happens to be, times the derivative of our inner function, and that's going to give us 3 times 1 over x, or 3 over x. Okay, so as it turns out, we see a multiple of 1 over x, which is actually there. So as it turns out, maybe we could do a substitution like that, because again, we see something related to a function that's already there in terms of that derivative. What do we mean though by use a logarithm rule though? What's a logarithm rule that could apply here? Well, one of the rules for logarithms says that if we have an exponent inside of a logarithm, we can actually pull it out front and it becomes a factor, it becomes a coefficient for that logarithm. So another way of writing this problem would be 3 times the natural log of x over x integrated with respect to x. And so the benefit of using that logarithm rule is we take something that looks like a nested function and we turn it into something that very much is not a nested function. So we could use this substitution if we want, that's certainly an option, or we can use the simpler version here and then do the same kind of substitution, but do it with simpler numbers essentially overall. So let's use the simpler version. So I'm going to allow u to be the natural log of x. And again, why can I do this? Well, I know this function has a derivative of 1 over x, and I see a 1 over x right here. I see technically a 3 over x, but if we forget about the 3, we can just think of it as 1 over x and then a multiple of that. So that means du dx is going to be 1 over x. Okay, so similar to what we had above, just differing by that constant 3. And so then our differential du is going to be 1 over x dx, and our differential dx is going to be x du. Either way, we can substitute and we can simplify this and write everything in terms of the new variable. Okay, So doing our substitution, we have a 3. We have natural log of x, which we're replacing with u. Now I'm going to write the 1 over x separately, okay? And then we're replacing our dx with the expression involving du, which will be x du. And again, the benefit here, based on our formula for substitution, how we do that, the remaining expression involving the old variable is eliminated, leaving us with the antiderivative of 3u du. Now, if we so choose, we can factor out the 3, or we can just use the power rule, and then whenever we use the power rule and divide by the new exponent, we'll just make sure that 3 is divided by that new exponent. So let's just try it that way. So we're going to raise our exponent 1 to the next power, which would be 2, and then divide by that new exponent. So that's going to give us 3/2 u squared plus c. And then we're going to resubstitute with natural log of x. So that's going to be 3/2 times the natural log of x squared plus c. Okay, let's try one more example, and then we're going to look at a definite integral. What happens when we have limits of integration? Well, the good news is not much changes. We just have a couple more steps at the very end of the problem. Okay, so we want the antiderivative of x times e to the x squared integrated with respect to x. Okay, well, where's the nested function here? I see an e to the x squared. That looks like a nested function. So e to a power is one function, and now inside of that we have another function, x squared. So if we're going to think of x squared as our inner function, we need to be able to see the derivative of it in the problem in order to substitute for it. So the derivative of x squared would be 2x. Okay, well, I don't see a 2x, but I see an x, so that's good enough. As long as I see a constant multiple of whatever my derivative would be, then we're good, and the constants will just take care of themselves. So I'm going to substitute for x squared, so I'm going to allow u to be x squared. I'm going to differentiate in order to get my differentials. So du with respect to x is going to be 2x. So that means du is 2x dx, and dx is equal to du divided by 2x. Okay, so we can replace our exponent with the variable u, and then we can also substitute dx. So we have the antiderivative of x still left over times e to the u, and then dx is now du over 2x. Okay, the remaining expression involving x divides out, is eliminated, which just leaves us with that 2 in the denominator, which is not a problem. So 2 in the denominator is same thing as a factor of 1/2. So we have 1/2 times e to the u integrated with respect to u. Well, we know the antiderivative of e to the u, just as it is its own derivative, it's also its own antiderivative. So the antiderivative of e to the u is just e to the u. And 1/2, that constant coefficient, does not make a difference when it comes to differentiating or anti-differentiating. So our antiderivative is 1/2 times e to the u plus c. And so now we resubstitute, and that's going to give us 1/2 times e to the x squared plus c. And that is going to be our antiderivative. Okay, so for our final example, let's see what happens when we have to calculate a definite integral. Okay, and again, not much changes. The strategy is the same. The only thing that we have to remember is once we make our resubstitution at the end of the problem after we integrate, then we have to make sure that we don't forget that there were originally limits of integration, and we need to apply those. But again, keep in mind, we cannot apply them until we're back in terms of the original variable. So once we change over to the variable u, those limits of integration don't actually apply. They only apply to the variable x, so they're only plugged in when we're back in terms of the variable x. Okay, so we have a nested function. We have the fifth root of a function of x. Well, we know we don't really have a radical rule, but we know there is a rule that allows us to deal with radicals. So let's go ahead and rewrite this in the way we would need it to look in order to use the rules that we have. So a fifth root is the same thing as a 1/5 power. And so this is the function that we're integrating with respect to x. So now we have an inner function inside of the function that takes an input and raises it to the 1/5 power. So ideally we'll substitute for 1 minus x squared. But first we need to verify, do we have the derivative of our inner function present in this problem? Well, the derivative of our inner function would be negative 2x. And I don't see a negative 2x, but at least I see the x. I see 12x. So I see some multiple of my derivative. So that means we're good to substitute using this as our inner function because we have a multiple of its derivative in the problem. So I'm going to allow u to be 1 minus x squared. I'm going to differentiate with respect to x, which is going to give me, again, negative 2x. So that means du is equal to negative 2x dx, and dx is equal to du divided by negative 2x. Okay, so I can substitute for my inner function. I can substitute for dx. And at this point, I'm going to go ahead and drop off those limits of integration. Don't forget about them. So maybe star this point in the problem. So we know to come back here and reference our limits of integration again. But as soon as we start changing variables, those limits of integration no longer apply. So we're just going to look at the indefinite integral first. So we have 12x. Now we're substituting u. So it's now u to the 1/5 power. And then we're substituting for dx, which is going to give us du divided by negative 2x. Okay, our x's divide out, and then our constants are also going to reduce as well. So 12 divided by negative 2 will leave us with a negative 6. So when we change our variables, we have negative 6 times u to the 1/5 integrated with respect to u. And so now we can take our antiderivative using the power rule. So it doesn't matter that it's a fractional exponent. We're still going to increase that exponent by 1 and then divide by that new exponent. So we have negative 6. Now we're dividing by the new exponent. So if we were to take 1/5 and increase it by 1, that's the same thing as adding on 5 over 5, which is going to give us 6 over 5. Okay, so that's going to be the new exponent. We are dividing by that new exponent. Now normally we would add on the plus c once we take an indefinite integral. But remember, we have limits of integration. And as we determined in a previous video, once you have limits of integration, you're actually evaluating your antiderivative with specific values of x. The constant of integration doesn't actually matter because it's just going to disappear when we plug in those limits of integration. So we don't actually need it at this point. So all we really need to do is just clean this up and then resubstitute and evaluate with our limits of integration. So negative 6 over 6/5. Well, remember, dividing by a fraction is the same thing as multiplying by its reciprocal. So we could write that as multiplication by 5 over 6. And if we want to go ahead and resubstitute in this step, we can do that as well. So that's going to be 1 minus x squared raised to the 6/5 power. So one more simplification. Our 6's are going to eliminate, which will just leave us with a negative 5. So we have negative 5 times 1 minus x squared raised to the 6/5 power. Now, let's go back to the original problem. We wanted to integrate from x equals 0 to x equals 1. So now we will apply our limits of integration. We're evaluating from 0 to 1. In other words, imagine the original function representing its graph. Excuse me. And imagine finding the area under the curve from 0 to 1. That's essentially what we would be doing at this moment. So I'm going to evaluate this with an input of 1 and then evaluate with an input of 0 and subtract the 2. So that's going to be negative 5 times 1 minus 1 squared raised to the 6/5 power, okay, minus negative 5 times 1 minus 0 squared raised to the 6/5 power. And don't be alarmed about the exponent. If it makes you feel better, we can always plug in each of these to our calculators, but as it turns out, that's not really necessary here, and we'll see why when we do plug it into the calculator. So let's see if we can evaluate this whole first expression in the calculator. So we have negative 5, and we're multiplying it by 1 minus 1 squared. And that is then being raised to the 6/5 power. So what does that come out to? It comes out to 0. Why does it come out to 0? Well, 1 squared is going to be 1, and then 1 minus 1 is 0. It doesn't matter that the power is 6/5. Anything that is 0 to a power is going to be 0. So 0 to the 6/5 is 0. 0 times negative 5 is 0. So everything in the first set of brackets comes out to 0. Minus whatever we get in our second set of brackets. So something similar kind of happens here. So we have negative 5 times 1 minus 0 squared, and that is then raised to the 6/5 power. And that's going to come out to negative 5. Well, again, why did something that looked so complicated come out to something simple? Well, 0 squared is just 0. 1 minus 0 is 1. 1 to any power is still just going to be 1. So 1 to the 6/5 power is just 1. Times negative 5 is negative 5. And so those double negatives will change to an addition. So our final answer is going to be 5. So that gives you several different examples of what substitution can look like. Substitution can be very straightforward in the sense that if you start with a function where you already see an inner function and outer function and exactly the same as the derivative of the inner function, like we did for our first two examples, substitution can be fairly straightforward, and once we substitute, the antiderivative rules apply like normal. We can also see situations where maybe we don't have exactly the same thing as the original derivative, but maybe we have something like x cubed versus 4x cubed. As long as we see the same expression in x, regardless of the coefficient, we can use that particular substitution. So we're looking for multiples, constant multiples of the derivative. We may have the exact derivative of our inner function, or as long as we have a constant multiple of it, substitution will work in the same way. Now the natural log function, in this case, we had an outer function and an inner function, but the inner function wasn't really going to work in terms of a substitution. So with something like the natural log, or any function that is, focus more on what you know about functions and their derivatives. You're looking for some function in the problem as well as its derivative. If you can find a function that's then complemented by its derivative, then that's usually going to give you an indication of what you're substituting for. And as we saw in this last example, finding a definite integral, not that different from finding an indefinite integral using substitution. We just have to remember to substitute our limits of integration at the very end once we're back in terms of the original variable. So the substitution technique for integration is going to be very powerful. It's going to allow you to integrate a lot of new functions that otherwise we didn't really have a strategy for before. And practicing with this is going to be really important. recognizing what's inner, recognizing what's outer, and then knowing how to find your substitution value and how to substitute for your differentials from there.